This is the third installment for intermolecular forces as well as solid forces and their effects on overall macroscopic properties. Here's a summary of the first 2 days of what we were looking at. We have intermolecular forces, collectively known as van der Waals forces, and we had talked about the mixtures with ions, polar molecules, and nonpolar molecules having either ion-dipole, dipole-dipole attractions, and dispersion forces. Dispersion forces, again, also being called London forces. And the specific type of dipole-dipole attraction that has hydrogen attached to nitrogen, oxygen, or fluorine, which are the most electronegative elements on the periodic table, are called hydrogen bonds. Again, there's a generic trend of going from strongest to weakest that is listed on the screen. Again, is a generic trend, and you should make sure you're paying attention to any data that is provided to make sure that you are answering the questions effectively, because it is just a general trend. There are some dispersion forces that will be stronger than dipole-dipole, which can even be stronger than hydrogen bonds, depending on the molecules that you're comparing. So other than intermolecular forces, what else makes up a solid? Well, there are quite a few other forces other than just IMFs that are involved in solid substances. So you'll notice based on this diagram that the intermolecular forces in that purple diagram that we just reviewed is just this one little box down here in the corner, and everything else when it comes to solid forces is now structured in front of you. You might be thinking, if we've just spent 2 days summarizing intermolecular forces, how long is it going to take us to cover everything else? Surprisingly, not that long. The amount of detail that we're going to go into for the other types of crystalline solids and amorphous solids are not going to be nearly as detailed as the intermolecular forces. So what you see in front of you is pretty much what you would need to know, as well as, of course, some details about the individual ones. But everything that we've spent so far is actually in discussion for this one box down here in the corner, and we're now going to take a look at the differences between solids. So let's start off with amorphous versus crystalline. Crystalline means that the particles within the solid are in an organized fashion. They are in what is referred to as a crystal lattice, and there's a very organized, almost grid-like pattern to them. Amorphous means that there's no real shape or consistent shape to it. And here are two examples of both of these are silicon dioxide. The one on the left is glass. The one on the right is quartz. You'll notice that the more organized, or the crystallobate, I can never pronounce that correctly, but the crystallobalite is quartz. You'll notice the organized structure of that is considered a crystalline solid, where glass on the right-hand side is not necessarily having a regular pattern. Those connections are still very strong with each other. However, they are not nearly as organized, and so when they're more organized, it will have a higher boiling point. The lower boiling point will be associated with the non-organized variety. Network covalent structures. Network covalent structures are consistent, repeated patterns that are all connected by covalent bonds. So really, let's start with the example of diamond here on the far left. Diamond are going to be carbon atoms that are tetrahedrally connected to each other consistently across the entire thing. So if you have one perfectly made diamond, that technically is one molecule. So that entire big structure would be made of millions upon millions of atoms of carbon in an organized fashion, all connected to each other in one ginormous molecule. It's all one big network of covalently bonded structured atoms. So hence the term network covalent bonding, or network covalent structures. That's what gives diamond its high boiling point. If you're trying to actually, or melting point for that matter, if you're trying to change diamond, it's very difficult to do. It has such a high boiling point because all of those molecules or all those atoms are attached to each other in one big molecule. Same thing is true of quartz, which you just saw on the previous page, which is this structure here. It is also in a tetrahedron style fashion. Silicon carbide is a slightly different structure. And then graphite, which has a lower boiling point than diamond. By the way, graphite and diamond are both just carbon, just different crystal structures of it. As far as graphite is concerned, this is why you have your pencil lead. And as your pencil lead is able to work, is as it writes on a page, it basically removes sheets upon sheets of those layers to each other. So looking at graphite specifically, this top layer here, that one sheet, is a network covalently connected structure. If you look at the sheet underneath it, it's also a networkly covalently connected structure. And then these sheets are attracted to each other through intermolecular forces. So the sheets themselves are held together by network covalent structure, while the connections between the sheets are intermolecular forces. So when you go to write on paper, what happens is that you layer, one of those layers comes sheeting off and attaches itself to the paper itself, and it has an intermolecular attraction to the paper. So you're just removing layer by layer by layer. Granted, that does not work in diamond because it's not in sheets. All of these structures form very high melting point materials. They are generally hard materials, and it also means that they're going to be brittle. In other words, if you hit them, they will shatter. They don't just start to bend or fold. As far as some additional memorization, I do strongly recommend that you know that carbon and silicon as elements both form network covalent solids, and silicon dioxide is a network covalent solid where it would be either glass or quartz. While there are others, these are the key examples that I have seen used in essay questions or in certain questions from different exams. Ionic solids. Ionic solids we have talked about before, where you have a regular repeated pattern of positive and negatively charged ions that set themselves up in a lattice. Because they are all connected in that fashion, it does, again, create a very high melting point for most ionic solids. They are brittle, meaning if you hit them with a hammer, they will shatter. So for example, if I were to, let's say, take this column of ions that I have right here and try to shift each one of them down by one spot, what would happen is that the purple and the purple would be next to each other, which are the currently, let's just say, positively charged ions. And when those positively charged ions get next to each other, they're going to repel. Same thing with the green versus against the green. If you were to shift each of that first cell down by one, there would be such a strong repulsion that it would basically just rip apart and pull apart, which is why salt crystals are brittle. Hit them with a hammer, they break. They do have that high melting point because there is a strong attraction for those ions for each other. The stronger or the higher the charge of the ions, generally the stronger the attraction for those particles to each other, which is what would explain crystal lattices with higher ion charges having higher melting points. These are non-conductors of electricity, because bear in mind, these ions, once they're in this structure, they cannot move. If you were to dissolve that structure into water, then those ions would have the ability to move and conduct electricity. However, in the solid form, they do not conduct electricity because the ions do not have the ability to flow. Metallic solids. So the definition of a metallic bond is where you have a group of positively charged metal ions swimming in a sea of valence electrons that are not particularly bonded to any individual atom. Let me clarify that a little bit better, where you have metal ions in a sea of electrons. So taking a look at this bottom picture on the right, let's just say that each one of these are silver atoms with their valence electron that's sitting here. And that's a silver atom with its valence electron. There's silver atom with its silver ion with its valence electron, and each of those are attracted to something. If we're looking at this one electron, does that one electron belong specifically to one of those four ions around it? Well, there's no real good way to tell. which one it would actually belong to. So if it's loosely held, if those electrons are loosely held, it could belong to any one of these 4 ions around it, or silver ions around it. So with that, what type of properties come about from it? Well, this would allow silver to be malleable. If you hit this with a hammer, it could just bend and fold into shape, and it doesn't really matter. Also means they're ductile. Ductile means you can pull them into wires. So malleable, you can be flattened into sheets. Ductile would be pulled into wires. These are also good conductors of electricity. So let's say I had an extra electron and I toss this electron into this mix. Well, that electron would repel this one, which would repel that one, which would repel this one, which could repel that one, and which would repel this one, and eventually knock that one out the other side. So now I've got an electron that if I toss into one end, comes out the other, which means I have flowing electrons. So by adding an electron to a metal that ends up adding too many electrons, you basically cause a domino effect where one of those electrons can spit out the other side. So if you're constantly pushing extra electrons through one end, you are going to get electrons coming out the other side of it as well. Granted, you will have some resistance where some of those electrons will travel off to the outside edges, which then gets you into physics of talking about resistance in wires and etc. We're not going to go there here. At the moment, all we really need to know is metals conduct electricity well because of the way their electrons are structured in their metallic bonds. Melting points for metals vary. It'll depend on the attraction that it has for each other. There are definitely some metals that are extremely high in melting point, like tungsten, which is the highest melting point for metallic elements. And then you got low temperature ones like mercury, which are liquid at room temperature. So the melting point range is pretty vast between metallic solids. But again, as a quick review, all of this can be summarized by the fact that they have good conductors of heat, they're good conductors of electricity, they're malleable and ductile, and but their melting points are variable, depends on their level of attraction. So overall, what we were looking at is a summary of the solids for network covalent solids, metallic solids, ionic solids, and molecular solids. The ones that are held most loosely together are the molecular solids, since there's not as strong of attraction between each of the molecules themselves. Not to say that you can't have high melting points with those. It's again, you really have to look at data. However, these are oftentimes referred to as the weakest. Network covalents are the strongest. Ionic solids are the second strongest, and metallics are generally considered the third strongest. Where are you going to find them on the periodic table, or if you're trying to figure out which ones are doing what? Metals are the easy ones. Metals are metals. If you know where the metals are on the periodic table, they will be metallic solids. Also, alloys will form metallic solids as well. The network covalent solids are the carbon and silicon, which is, and also gallium can do it as well, but not nearly as well because it generally, gallium goes more toward the metallic variety. But network covalent solids of carbon and silicon, don't forget silicon dioxide, are the 3 major ones you should memorize. Those are where you'll find them in the middle of the periodic table there. Molecular solids are, well, first thing you have to do is make a molecule, and molecules are made up of covalent bonds, and covalent bonds generally happen between 2 non-metals. So you'll notice I connected the hydrogen on the left of the periodic table with all of the non-metals on the right-hand side of the periodic table to mention the molecular solids there in purple. And then last but not least, ionic solids, which are a mixture of metals and non-metals together. All right, so overall, in summary, I am going to put pauses in the presentation to make sure that you have an opportunity to copy all of this down. You'll notice that the types of solids are either amorphous or crystalline, and the type of crystalline solids are network covalents, which are generally considered the strongest, ionic solids, metallic solids, and molecular solids. Molecular solids in general are the weakest, and the molecular solids are held together by intermolecular forces, and that set of intermolecular forces was summarized by the first faculty of notes. I'll give you a moment to copy that down if you need to. Where to find each of those is, again, we just looked at those a moment ago, but again, if you need to copy this down, the molecular solids are made up of molecules that are made up of two non-metals or more connected together by covalent bonds, but their molecules are attracted by intermolecular forces. Metallic solids are where metals are attracted to other atoms of metal that are held together in a metal ions held together in a sea of valence electrons that are not tightly held by any individual atom. The network covalent solids are the carbon, silicon, and silicon dioxide, which generally are going to form the strongest types of solids or the hardest type of solids. They are brittle, and they do have the highest melting points in general. And then ionic solids, mixtures of metals and non-metals. Here is a summary list of the different types of solids, giving also examples of each, as well as a good summary of the different properties. And here is a summary of the intermolecular forces that we discussed on the first few days of this information. Again, intermolecular forces called van der Waals forces. There's generally two major varieties of dipole-dipole and dispersion, which would be broken down between polar molecules and non-polar molecules. If it is a mixture with an ion, it'll be an ion-dipole combination. When you're looking at intermolecular forces of molecular solids, the boiling point and vapor pressure and melting point and surface tension will be due to the intermolecular forces. The stronger those intermolecular forces, the higher the boiling point, the lower the vapor pressure, the higher the melting point, and the stronger the surface tension. That really concludes everything we've got up to this point. I will be posting this presentation either on my website or in Google Classroom, so students can use this as a means of review. If you have questions, please let me know.